This is Abigail Stehno, and I'm going to present the methodologies that were applied for the Sabine to Galveston coastal flood hazard analysis. My teammates include Jeffrey Melby, Chris Massey, Shubhra Misra, Noberto Nadal Caraballo, Alex Teflonitis, Patrick Lynette, and Victor Gonzalez. The Sabine to Galveston study regions include 100 kilometers of coastal storm risk management consisting of levees, floodwalls, pump stations, and closure gates in the Freeport, Port Arthur, and Orange County vicinities. In order to develop the joint probability model, historical storms were used. The figure on the left shows tracks of all historical tropical cyclones that are in the HRDAT database dating back to 1938. The figure on the right has only the storms that made landfall in the northern half of Texas and provides an idea of the spatial density. All of the storm probabilistic analysis was based on the coastal Texas study work, and Noberto Nadal Caraballo led that JPMOS study. This diagram shows the close relationship between CSTORM, StormSim, and the coastal hazard system. We start with efficient storm sampling using modern data sampling techniques in the HRDAT database. A JPM model is created of tropical cyclone parameters and then efficiently sampled to create a suite of synthetic tropical cyclones that encompasses practicable probability space. These storms are modeled with a climatology model to produce winds and pressure fields, and then modeled within CSTORM to quantify the storm water levels and waves. The statistics of the responses are computed, including epistemic uncertainties, and then the model outputs and statistics are stored and distributed in the coastal hazard system. The overarching goal is to define the response using this joint probabilistic modeling approach. Tropical cyclones are treated using the typical joint probability approach, where a probabilistic model of the cyclone parameters is defined. Then the response probability can be computed using that probabilistic model. The storm response is a function of the reference location, central pressure, radius of maximum winds, forward speed, and heading direction. This equation suggests that any response exceedance distribution can be determined as a function of the conditional joint distribution of the storm parameters and the storm rates. The epsilon term here represents the sum of all epistemic uncertainties. For extratropical storms, we use the peaks over threshold methodology with the addition of a high-frequency cutoff to avoid introducing tidal fluctuations. The extratropical hazard in Texas is small, so only tropical storms hazards were considered for S2G. 660 synthetic tropical cyclones were modeled for the Coastal Texas Comprehensive Study, effectively mapping the practical probability space using the JPM. The image on the left shows the synthetic storm tracks. The image on the right shows the synthetic modeled storm parameters for one of the coastal Texas storms. The storm intensity, which dominates the storm response, is fairly consistent over most of the storm life until about 90 nautical miles from the shore, where it begins to infill and decay. This behavior is consistent with historical storms. Within the CSTORM modeling, a new LiDAR DEM was built. The meshes were refined around the project areas, and structure crests were modified for the with project conditions. Results were validated using high water mark and gauge storm water level measurements. 3 relative sea level change scenarios were considered, associated with the beginning of service life in 2027, a 50-year service life for 2077, and the 100-year service life of 2127. Relative sea level change includes eustatic sea level rise and local changes in ground levels, which are mostly due to subsidence. The relative sea level changes were included in the ADCIRC water levels, with the geoid offset that also included steric and datum adjustments. StormSim is a suite of coastal engineering, statistical modeling, and stochastic simulation tools that have been developed over the last 15 years by our group. This is an overview of the StormSim capabilities, which include hazard analysis, response computations, multiple simulation methods, and meta-modeling. StormSim capabilities developed for the S2G analysis include runup, overtopping, and wall responses using a non-life cycle peaks response-based simulation. This approach is fully probabilistic with multivariate probabilistic forcing and associated uncertainties carried through the design process, along with uncertainties associated with the empirical equations used to compute the responses. Stochastic approach for the S2G began with the optimal subsampling of the 660 storms to create a reduced storm suite of 189 storms. Each of the storms was sampled hundreds of times, uncertainty was applied by storm, and the response was computed by storm. Uncertainties included aleatory and epistemic uncertainties. The response distributions are then computed and limit states are evaluated at specific statistics and quantiles. This approach maintains the integrity of both the nonlinear processes and the underlying complex joint probability of forcing. So the understanding of risk is defined at a specific statistic is consistent across the entire project. We computed wave runup, wave overtopping, combined overtopping and overflow when the freeboard is negative, pressures on the walls, and geometry of the overtopping nappe, among other things. Empirical equations from the Eurotop manual and Steve Hughes were used for the overtopping calculations. The combined GOTA, hydrostatic, and hydrodynamic wave pressure distributions are diagrammed to the right, and Hughes nappe geometry, velocity, and force associated with steady flow overtopping is diagrammed on the bottom. The maps show the locations where the structures were analyzed as small yellow hash marks on the coastal storm risk management. The plot shows some of the example diagrams of the structures that were analyzed for S2G. For the levees, an idealized geometry was created for the LiDAR measured transects for every single analysis location for the without project conditions, shown in blue. The existing levee geometries did not have a nice linear slope, so we incorporated a slope analysis using the idealized without project geometries that weighted the slopes over a vertical distance corresponding to the storm water level, plus or minus 1 wave height for each of the probabilistic storms. The red lines on the levee plots represent the geometry of the feasibility authorized structure. Limit states based on a serviceability, start of damage, and survivability were defined at the 1% annual exceedance probability. These general criterion are from the Coastal Engineering Manual and are consistent with those used in other projects. The start of damage refers to the impact on surrounding soils near the structure due to overtopping, but does not include settlement, damage to the wall, or geotechnical failure. Damage was defined only in relation to erosion on the lee side surrounding soil that supports the structure. The hazard curves for the storm water level and wave heights, as well as the overtopping response hazard, was compared for the without project conditions and the with project conditions for each of the transects. For this case, the wave height and water level hazard curves for the without and with project conditions are barely distinguishable. As you can see here, the increase in structure crest elevation reduced the overtopping rates in the right-hand plot, where the solid lines are for the with project overtopping rates and the dotted lines are for the without project. In this particular location, there wasn't a difference between the without project and the with project forcing hazards, so this overtopping reduction is completely due to the structure modification. This is an example of a typical output table that we produced for the Galveston district, our sponsor. This shows the overtopping rates for a range of annual exceedance probabilities at a 90% confidence level. The black numbers are below the overtopping limit states, red numbers exceed the serviceability limit states, and purple numbers exceed the survivability limit states. So for to say transect 148, the crest elevation of 21 feet is adequate at the 1% AEP to resist sea level rise condition 0, which corresponds to the start of the project. But for sea level rise condition 1 at the 50-year service life, the serviceability limit state is exceeded at the 1% annual exceedance probability. For sea level rise condition 2 at the 100-year service life, the survivability limit state is exceeded at the 1% annual exceedance probability. Optimized crest elevations were based on a no damage limit state by computing the overtopping rate for a relatively low crest elevation and step increasing the crest elevation until the 1% annual exceedance probability overtopping rates were lower than the prescribed limit states at both a 50% and 90% confidence level. The responses for different crest elevations were analyzed at each of the analysis areas. They are shown for the respective floodwalls on the right and the levee on the left. Starting from the bottom, we analyze the existing elevation, which is taken from the LiDAR data. The seaside slope of the existing levees were a weighted average over the length of the slope on which the waves and water levels acted. Just above that in purple is the feasibility elevations that were authorized for construction by Congress. The orange is the optimized elevations we computed during the PED study that just met the overtopping limit states for SLC1. The more accurate design methods typically increase the PED wall and levee elevations over the feasibility elevations. This was a combination of more accurate wave and water level modeling and response and statistical modeling across the board. An adaptability elevation was analyzed for resilience. The adaptability elevation for feasibility was 2 feet over the authorized elevation. The adaptability for optimized corresponds to the elevation that just met the limit state for SLC2. This adaptability elevation was used for the final design of critical features such as pump stations and gates. The pictures are of existing floodwalls and levees in the study region that have been exposed to the forcing hazards. In all, we looked at 291 different analysis locations, which included 112 in Port Arthur, 97 in Freeport, and 82 in Orange County. At each analysis location, we analyzed 7 crest elevations, each under 3 sea level scenarios. 13 different forcing and response hazards were computed, depending on the structure type. And as of right now, we have 15 reports and papers. That's all. Thank you for joining in today.